Okay, thank you. Thank you, Thomas. And hello, everybody. Nice to see you a lot here in our Euroworks. And I would like to start presentation with invite Maria Kortesniemi, and she is assistant professor of food chemistry and food development in University of Turku. Welcome, floor is yours.
Thank you. Good morning. I will start by sharing my slides. So, is this okay?
Okay.
Yes, we see.
Great. So, good morning, and I guess good afternoon to some of you. So, I'm Maria Kortesniemi. I come from the Food Sciences Unit at the University of Turku, Finland. And I'm here to talk about the effect of cultivar and latitude on sea buckthorn metabolites. So you may know that University of Turku has a very long history in sea buckthorn research, over 30 years of experience in the field, and this is mainly thanks to Professor Heikki Kallio's work and also Professor Bauru Young's work. Heikki especially, you probably know him, has published over 70 sea buckthorn related publications during his academic career, and he's still continuing, even though he should be retired already. But he's very active in the sea buckthorn field still. And in this word cloud, you see some of the main themes of the research that has been conducted in Turku. So a lot of different angles to the sea buckthorn, spanning the basic sensory relevant compounds, sugars, acids, and lipids, which are relevant for the health effects of the sea buckthorn, and especially the sea buckthorn oil. We have studied the health effects in different clinical trials, and also this latitude aspect, the effect of foraging and the different cultivars has been always one of the kind of the core areas in the research as well. So the latitude itself is not that of a factor here, but of course, different growth conditions that are related to latitude are important for plants, obviously, and the growth conditions can vary at different latitudes. And what the latitude mainly does is it affects the length of the growth season, the day length, the intensity and quality of the light, and temperatures prevailing at each side of cultivation or growth area. So especially in the northern latitudes where we are located in Finland, so the angle of the solar radiation is also a very important factor and unique to these northern latitudes. And because of these more, should I say, extreme conditions in terms of the growth conditions and the light regime, plants can suffer from abiotic stress. So this affects the metabolism of the plants, which then can be seen as changes in the chemical composition of, for example, the sea buckthorn fruit. And we have studied the effect of latitude by having same genotypes or same plants that have like a similar genetic background grown in different locations where they produce different phenotypes despite of the genetic similarity. And this phenomenon is called plasticity. And as I mentioned, the Nordic conditions have this extreme light regime, and also the high latitudes in the north correlate with the cooler climates and long photo periods, especially during the like the nightless night, as we call it, during the summer. So the sun doesn't set in the north. So these extreme conditions especially have a high impact on the plants and their metabolism. And when grown in these kind of stressful conditions, it typically promotes the biosynthesis of secondary metabolites, which act as protecting compounds against UV light and different temperature variations. What is also related to the Nordic conditions is that, which can be seen as a positive side, is that the cool climate and the winter conditions can also be associated with the lower prevalence of pests and the need for their control. And so far, if we look at the sea buckthorn fly situation in Finland, in the south we have some cases of the fly, but not in the north, and hopefully it stays that way, that it doesn't get worse. Here you see the map of Finland. So we are located between the 60 and 70 degrees northern latitude. And here you see also the test fields we have studied. So we typically compare the Finnish cultivars Terhi and Tytti. They are subspecies Rhamnoides, and they originate from the Finnish wild sea buckthorn. So we have studied the effect of latitude with these cultivars in Turku in the south. Here, and in comparison to same cultivars grown in Kittilä in the north at 68 degrees of northern latitude, where we have had test fields since 2003. And here you also see on the red font the wild sea buckthorn berries we have studied in Uusikaupunki, Kemi and Taapajärvi at 3 different locations. And also the other marked locations are newer test fields we have, and also fields that we have access to in research-wise if needed. And here these 3 maps show that how the growth conditions vary along this span of Finland's length from the 60 to the 70 degrees northern latitude. So you see the gradient of the duration of the thermal growing season, as well as the degree days, which means like the effective growing temperatures, and also the differences in the precipitation or the rainfall in these different areas. In addition to these older test fields we have had for over 20 years. We have recently established new test fields as part of this Tyrniraki project. So we have 5 new test fields here in the south, near the riverbanks or close to the sea in southwestern Finland. And also we have established the northernmost sea buckthorn test field in Utsjoki here at 69 degrees of northern latitude. In this table, you can see also the conditions that have taken place in these different growth locations we have studied. For the wild sea buckthorn, we have compared the berries grown in Uusikaupunki, Kemi, and Taapajärvi. You see that the Uusikaupunki in the south has a higher degree days and the global radiation, whereas in the north, the numbers may be even close to half of what can be reached in the south. And also for the Tytti and Terhi cultivars in Turku and Kittilä, we see that in Turku in the south, again, the degree days and global radiations are much higher than in Kittilä. So basically the degree days symbolizes the total energy available for the crop for its growth, and it's defined as the sum of the values exceeding the threshold value of 5 degrees daily. So as we study the sea buckthorn metabolites, we have applied this NMR metabolomics tool. So NMR stands for nuclear magnetic resonance spectroscopy. And basically metabolomics is a study where we have a look at the different metabolites at a given time in the sample. So we basically take a snapshot of the sample, and we can examine compounds that belong to different compound classes at the same time. So both primary and secondary metabolites given the right sample preparation. And in case of the sea buckthorn studies we have conducted, we have looked into the water-soluble metabolites, which include amino acids, sugars, sugar alcohols, organic acids, and vitamin C. And vitamin C, for example, you know, it's a very important quality factor in sea buckthorn. But I also like to point out the benefits of this method over to basic methods we typically use for analyzing sugars and sugar alcohols, is that we can also see the amino acids in the same measurement. And amino acids are relevant, for example, in terms of the processing of sea buckthorn. So whenever amino acids are reducing sugars like glucose and fructose are present, and the mixture is heated, so there's a risk of forming acrylamide and other Maillard reaction products that might or might not affect the quality of the processed product. Yes. So that was metabolomics in very brief. So here examples from the metabolomics research. So multivariate modeling is how we analyze the data typically. And on the left, you see the results from the wild sea buckthorn grown in 3 different locations in Finland. So you see that, for example, in Uusikaupunki in the south, these samples correlate with the higher humidity of the growing place and high radiation and high temperature. And the metabolite that is associated with these conditions is ethyl glucoside. So this compound is typical for this subspecies Rhamnoides, and it's especially abundant in the berries grown in the south of Finland. Then if we look at the Taapajärvi samples, which is the northernmost samples in this case, they correlate with the precipitation and the metabolites related to these growth conditions are quinic acid, ascorbic acid, and malic acid, for example. So acids are more abundant in the north in this case. Then if we move on to the Terhi and Tytti cultivars in this picture in the A model. So number 1 is Terhi and number 2 is Tytti. We see that quinic acid correlates with Terhi cultivar. So it's more abundant in quinic acid, whereas Tytti, the number 2, correlates with ethyl glucoside and malic acid, and also glucose and other sugars. So by this way, we can distinguish which are the key compounds that kind of are more typical to each cultivar. And similarly, we can compare the different locations, T for Turku in the south and K for Kittilä in the north. We see that in south, again, we have the ethyl glucoside here as a very dominating metabolite that correlates with the Turku samples, whereas in Kittilä, we have quinic acid, glucose, fructose, asparagine. So here we see that one of the amino acids is kind of being highlighted as an important metabolite, typical for the Kittilä grown samples. And we can maybe think that because of this difference, and we know that also the north-grown berries are more abundant in phenolic compounds, even though they were not studied in this case. I would say that the berries grown in the very north shouldn't be processed by heating in order to not to create the Maillard reaction products. So when there's glucose, fructose, and amino acids present at more abundantly, and also not to destroy the phenolic compounds. So in that case, the south-grown berries could be more, could be better option for processed sea buckthorn products.
5 minutes.
Thank you. We have also studied the sea buckthorn leaves in a similar manner. So this is just to show that also cultivar differences were found. So Tytti was more abundant in elagitannins and flavonoglycosides. And we have studied how the composition of the leaf changes during the growth season in different weeks. So from the start of the growing season, they are characterized with lipids and phenolics, whereas at the end of the growth season, they are more abundant in carbohydrates. And also we see differences in the leaves grown in the south and in the north. So this information can also be utilized in thinking if how we're going to utilize these leaves in processing or in different products. And then finally, I would like to introduce a bit more about this Tyrniraki project. So the idea here is to utilize sea buckthorn stands in nutrient sequestration in the archipelago sea drainage basins. So sea buckthorn stands have been planted between fields and rivers and seas. So their function is to catch phosphorus and nitrogen from the soil, and the sea buckthorn can be harvested and utilized. So hopefully less nutrients end up in the waters where eutrophication is an issue. So we have 6 test fields in this project covering over 3,000 plants. And here are some of the first results of the project. So we have studied the soil conditions. So soil is one of the themes today, but we have a lot of data collected, soil samples, but the analysis is still ongoing. But we see differences between the different test fields, and we will see how the soil conditions affect the sea buckthorn. Lastly, a few photos from the world's northernmost sea buckthorn test field in Utsjoki. You see the Nordic light conditions, very beautiful. And in Kittilä, we had the berries in 68 degrees north, and now we have 1 degree more towards the north. And we see after 2 years, we have already gotten berries, harvested berries from the test field. So we see that the sea buckthorn can succeed in these extreme conditions also in the very north. Here you see Norway. There's a river between Finland and Norway here, so we are very close to Norway. Yes, this is the summary. So northern growth conditions are typically associated with the relatively higher sugar content, acids, vitamin C, and the precursors for the secondary metabolites, namely the amino acids. And the ethyl glucoside formation is associated with the degradase and the global radiation, especially with the subspecies from Roinis grown in the south. And we also see that Tytti cultivar is more abundant in ethyl glucoside than this Terhi cultivar. And here on the right, you see a Tyrniraki farmer collecting the first harvests from the test field. And also we see that sea buckthorn can succeed in the 69 degrees of northern latitude. So this is my presentation. Thank you very much.
Thank you, Maria, for very nice and interesting presentations. And now we are open for questions.
Yes, Daria, may I ask a question? Okay. Thank you very much, Maria. Very interesting. I would only like to clarify, to understand right, 2 things. The first, you mentioned that you have a higher amount of blue radiation in the light. Compared to southern regions, the total amount of radiation is less than in south, what you get. Can you estimate the changes in the light composition by wavelength or so? And the second question is concerning your nuclear magnetic resonance analysis. Which protons are you using to identify the individual compounds?
Okay, I'll start with the NMR question because that's what I'm more comfortable with. So in NMR, we study the proton NMR, and if needed, we also can do like carbon NMR or 2D NMR, which is then usually used for identifying or determining structures, molecular structures of different compounds. But in metabolomics, the proton NMR is the mostly used.
Yes, the protons, what are bound to the oxygen or to the carbon, or what is where?
Yes, we can analyze all the protons that are attached to the carbon of each molecule.
Okay.
Okay, thank you.
Yes, and to the light question, yes. So I believe the blue light, which has more energy, is more prevalent in the northern latitudes, whereas the red light spectrum is more prevalent in the south, and it has a higher wavelength. So as the blue light has more energy, so it can cause more stress to the plants, but also it induces the growth. Yes, and also the angle of the sunlight or the solar radiation is very much different in the north. So I would say that like the total radiation is not higher in the north, but it peaks during the summer. So during the summer, the conditions are quite extreme.
Okay, thank you. I like to explain why I ask you this. Yes, because we some years ago started to do some experiments, not completely finished this work, where we tried to see if there are differences in the relation between the two chlorophyll isomers A and B in dependence on wavelengths. So we collected berries. I also know from Finland, but also from Greece and from other regions where the relation in blue and red in the light is very different. Yes, and you see some difference also in the chlorophyll, but the work is not finished. It has been not published until now. Thank you very much.
Thank you. That's interesting. Yeah.
Thank you. Any other questions? I don't see any in chat. Maria, can I ask about amino acids? Did you compare your results with other countries, for example, where could be grown your varieties?
Yes, actually, that's a very good question. We have compared Tytti and Terhi cultivars to those grown in Canada, Quebec. So we have those same cultivars grown in there, and also we have studied the subspecies sinensis from China in different locations, different altitudes. So those results are in the publications I referred to, but I only here focused on the Finnish results as the latitude was the focus here. So if you are interested, you can look for the 2014-2017 publication. So there we have those information.
Okay, thank you. And you found some big differences or know about chemical compounds inside?
Yes, the difference between the subspecies is very, very clear, especially using this metabolomics tool. And also the conditions in Canada are different, so it has a very big impact on the berry composition. I don't remember the exact details now, but yes, there are very big differences.
Okay, thank you. Any questions? Okay, I think it was very interesting presentations, and have a nice day for you and have a nice next research. And we are waiting for results about this last project, and I think it will be very interesting.
Yes, thank you very much.